Section 3-4, Measures of Relative Standing. The main idea here is to be able to compare a value with all the other values in the dataset. In other words, based on the value's location in the sorted dataset, what is the relative standing? There will be several ways to measure this: the z-score, quartiles, and percentiles. Let's take a look at some basics. Finding the z-score is one of the most useful ways to find relative position. They call it standardizing the value, and it measures the number of standard deviations away from the mean. Here are the formulas, one for the sample and one for the population. X bar or mu is the mean, sigma or s is the standard deviation. X is a value that you want to find. Then the result, z, is your z-score. So in order to use these formulas, you need the mean and the standard deviation for the dataset. Note the round-off rule is to 2 decimal places. This is because a lot of times we will be comparing these z-scores with other critical values that are already rounded off to 2 decimal places. One of the reasons to use z-score is to see how many standard deviations away from the mean it is. Back in section 3-3, we established the idea that values are unusual if they are more than 2 standard deviations away. With a z-value, we can actually make the comparison in terms of standard deviations. For example, suppose the mean pulse rate for adults is 67.3 beats per minute and the standard deviation is 10.3 BPM. Mr. Triola, our author, has a pulse rate of 48 BPM. Using the formula, we can compute the z-score, and it turns out to be a negative 1.87. Now if we look at the mean and standard deviation on an x-axis number line, we see that 48 would land with respect to the mean. It may be complicated to see this number line, so if we standardize it using the z-scores, we would have 0 as our balancing point that represents the mean. With a z-axis number line, we have a simpler stage for comparison. So now with our z-score of negative 1.87, we can easily see that this number is between negative 2 and positive 2. This makes the pulse rate, 48 BPM, an ordinary value. So Mr. Triola's pulse rate is not unusual. Another measure of position is the percentile. Many standardized tests, such as SATs and GREs, use percentiles to inform students of their relative standing compared to everyone who took the test. Percentiles break up the data into 100 parts. In order to find the percentile, we have to sort the data. Then we find the number of values that are less than that number and divide it by the total number of values. Multiplying by 100 will give you the percentile. For example, suppose we counted the chocolate chips for 40 cookies. If we look at the cookie with 23 chocolate chips, what is the percentile of this cookie? We see that there are several cookies with 23 chips. If we observe there are 10 cookies with less than 23 chips. Using the formula, we get 1/4 or 25 percentile. Now on the other hand, if you have the data set and you are given the percentile, you want to find the data value with that particular percentile or placement, you would use the locator function. It is important to remember that this formula gives the location. So if there are n values and we're looking for the value in the kth percentile, we take k divided by 100, then multiply by n. This value tells us where to look in the data set. If the locator is a whole number, then look for that value in that position. If the locator is not a whole number, then round up to the next whole number and select the value in that position. For example, if we look at those 40 cookies again and we want to find how many chips are in the cookie in the 63rd percentile, we use the locator function. 63 over 100 times n, which is 40. We get 25.2. Since this is not a whole number, we round up to 26 and look for the number in the 26th position. That number is 25. Another important measure of position are the quartiles. The quartiles split the sorted data into 4 equal parts. The first quartile, labeled Q1, separates the lower 25% of the data with the upper 75%. The second quartile, Q2, separates the data in half. Note that this is exactly the median. In general, we don't use the notation Q2 because we simply refer to this as the median. The third quartile, Q3, separates the top 25% from the rest of the data. A picture might illustrate the division into quarters, or 25% of the data. Other quartile-related statistics are the IQR, the interquartile range. This is simply the difference between Q3 and Q1. This measures the distance that encompasses the middle 50% of the data. The semi-interquartile range is half of the IQR. The mid-quartile is the average or middle numbers between the first and third quartiles. Note that this does not imply that this is the median. In fact, if the distribution is skewed, the mid-quarter and the median would be very different. The 10-90 percentile range measures the distance that captures the middle 80% of the data. Out of all these statistics, the one that is probably used most is the IQR. A common way to report the quartiles is the 5-number summary. This 5-number summary includes the 3 quartile measurements we saw earlier and include the minimum and maximum values. Sometimes the minimum values are called Q0 and the maximum value is Q4. In general, we report the 5-number summary with the minimum, Q1, the median, Q3, and the maximum. There is a nice way to display the 5-number summary that might reveal the distribution. That is the Boxplot. It is very important to draw the Boxplot to scale so it can reveal some important aspects of the distribution. To construct the Boxplot, we need the 5 numbers. Then we draw out a scale to help us keep the aspect ratio. Make sure the minimum and maximum values are included in the scale. The box is drawn with the boundaries created by Q1 and Q3. A line through the box would represent the median. The lines or whiskers extend out as far as the minimum and maximum values. Then we have the box plot. We generally want this labeled. Now if we take a close look at this graph, we can see that there is a large gap between Q3 and the maximum. This would signify a long tail on the right. This is why it's important to draw the graphs as much to scale as possible. For example, a normally distributed set of data would have fairly tight connections between Q1 and Q3, while the tails representing the max and min should be longer. A right skewed distribution would have a long distance between Q3 and the maximum. The close proximity between the minimum and Q1 and Q1 and the median would represent a bulging of data between 125 and 300. Continuing the ideas of a box plot, we can take a look at outliers. An outlier is a value that is far from the bulk of the data. The mean and standard deviation take all the numbers into account. Therefore, outliers can drastically affect these statistics. They can also affect the shape of the graph, like box plots. But box plots have a way to deal with outliers. In fact, it is a way of defining outliers. Think of the IQR as the base of the box for your box plot. Then 1.5 times IQR is about 1.5 of the base of the box. If we move this length to have it start from Q3, we can consider anything larger than this value to be an outlier. So anything larger than Q3 plus 1.5 times the IQR would be considered an outlier. Similarly, anything less than Q1 minus 1.5 times the outlier would be an outlier on the left side. Box plots can use this modification to show outliers. We can do this by using dots or asterisks to identify any points that would extend past 1.5 times the IQR. So the box plot whiskers would only go as far as 1.5 times the IQR on either side of the box. Here's an example of a data set that is skewed to the right with two outliers. The length of the line, or whisker, on the right side is 1.5 the length of the base of the box. So the 2 points are greater than 3 plus 1.5 times the IQR, would be considered outliers, and therefore be represented as points beyond the box plot. Wow, that was a lot. We have considered the basics of descriptive statistics. We have discussed types of data and the data collection, measures of center and spread, describing shapes of distributions, and a few other things. Our next task is to explore probability and see how that will fit into our study of statistics. This is the end of Chapter 3.